Welcome to Chapter 11. We will be doing electrophilic addition of alkynes. This is a review. You see that this is a multi-step. This is an example of a multi-step question synthesis. And so you have lots of different reagents, so you're not totally on your own, but you want to start thinking retrosynthetically. Okay, so how can you add an OH and an OCH3 onto a onto this molecule? What is your starting um, functional group? So you want to think of functional group transformations. So we just did um, the alkene reaction. So let's look at something like this, where you can do an alkene as your starting material. Make sure you get all your carbons. You have these 2 carbons here and 6, so 8 carbons. So there's 8 carbons. And an alkene would be a functional group that could add here. What would you do there? Yeah, so this is going to be, and you don't know this reagent yet because we haven't done oxidations, but MCPBA will make an epoxide. So this will make an epoxide. So metachloroperbenzoic acid is this, metachloroperbenzoic acid. Per means there's these 2 oxygens here. Okay, and so it's this oxygen that gets delivered. So when you have an alkene and you make an epoxide, you can do this reagent. This reagent is really nice. Typically it would be in the freezer, and it's like a little white solid, and it smells like fresh cut grass. So if you're running at a track and you're running laps around a track and you smell the grass being cut, that's what this reagent smells like. So this is a, a reaction that makes an epoxide from an alkene, and you're going to see that in our chapter 12. So this is a little bit out of order there, but it's okay, you can learn. So MCPBA is this. This is MCPBA, and it converts an alkene to an epoxide. So if you take an alkene, now we don't have any stereochemistry there because it's not an sp3. So if you take an alkene, there you go, that's an alkene, and you add MCPBA, metachloroperbenzoic acid, you're going to get this epoxide. And then what's happening here, and you do know this is an epoxidation opening, right? And the O, it's coming from the least substituted. So you want to have it as like sodium methoxide. You want this basic, you want a basic epoxide opening. So that would be, you wouldn't want it to be acidic. Okay, that would open from the other side. So sodium methoxide would work because of the regiochemistry in which this epoxide opens. Okay, so then the question is, so it's between A or B, and then the question is, how do you make this alkene from this alcohol? So let's look. How do you make this alkene? So the question now becomes, how do you go from there to there? Well, you're losing the OH. You know, OH is a horrible leaving group, not good leaving group. So one way we can make it a good leaving group is we can protonate it. Another way we can make it, so if we protonate it, it would look like this, OH2 plus. If we convert it to POCl2, it looks like this, OPOCl2. Cl2. Now, pyridine is going to come in and do an E2, because that's how we make, this has got to be elimination reaction. This is an E1. So what would an E1 give you? Well, this would leave, and then you would get a carbocation, because that's an E1. You lose your stereochemistry there. That would be a 1, 2, 3. That would be a tertiary, so that's fine. If it traded places, it would be a tertiary. But you do have this hydrogen here, the beta hydrogen, right? And then the beta hydrogen would give you the more substituted Zatsev's product. So you would get this alkene, okay? That's the alkene you would get from A. That's not the alkene we want. So this is going to be an E2. Remember in E2 as well, you might need to draw your chair, and you want your O, we can just write Lg, leaving group, and then this is a CH3 coming down. This would be a hydrogen, this would be a CH3 coming down here. The hydrogen is up, because see, this is down, and this is down. So that's down. And then here on this carbon, you would have a hydrogen axial and hydrogen axial. The pyridine would take this hydrogen and give you this compound that would be, we would call it the Hoffman E2 product. So this is an E2 product. So D is the answer. So this is a multi-step reaction that you need to think retrosynthetically with your reagents and start putting things together like that. All right, we're on chapter 11. We're going to deal with alkynes. Alkynes are very similar to alkenes. That's an alkyne, a triple bond, and it also undergoes electrophilic addition. So we're going to be adding substrates and different reagents to these carbon-carbon bonds. Now you're going to notice whether you have an internal or a terminal alkyne. An internal alkyne would be something like this. Okay, so that would be an internal. What would that be? 1, 2, 3, 4, 5, 6. 3-hexyne. That's internal. A terminal would be something like this, which would be 1-butyne. So that's a terminal. And this is an internal. And so you're going to see some reactivity differences there. Reactants are the reagents will be similar to the ones for the alkenes. So first of all, you got to see that you have an alkyne as a functional group, and then you can see that this is a terminal, and that's an internal alkyne. Be sure to try to draw this. This is an sp carbon, bonded to an sp carbon. They are linear, 180 degrees. So you can see how it's drawn as linear. This is a hydrogen. I would recommend you drawing a hydrogen on the terminal alkyne. These are CH3s. So this is 180. Try to draw as linear as you can. And you have 2 pi bonds. You have this pi bond here, an unhybridized p bond, and then you have one in the other plane as well. This is just showing you the thermodynamic strength of a pi bond. Short and strong, short and strong, short and strong. So this is going to be a shorter bond than a double bond, and then a single bond, and it's going to be a stronger bond. The naming, you add "-ine" to the end. You want to now, I'll give it also the lowest number, and you need to go through that carbon-carbon triple bond in your longest chain. So here, some examples of naming alkynes. This is numbered where the alkyne gets to be a 3 because you want to give it this lowest substituent. Here on the ring, it's going to get the 1. and it is actually a substituent. Here, this is a diene, so there's more than one, and here, 1 and 4. This is an ene and an ine. The ine gets the lower priority because it's going to be more reactive than an ene. Physical properties, we're dealing with van der Waals, intermolecular forces. So they're going to have low boiling points, low melting points. They're going to be soluble in organic solvents. The simplest is ethine. It's also a common name acetylene. It's used in high burning fuels to melt and shape metals. So you might have seen it, heard about it in there. That's also called ethinyl. Oral contraceptive. So this shows you the alkyne functional group in a synthetic estrogen that's used for the ethinyl estradiol. It's an oral contraceptive, and it keeps pregnancies from happening. This is another one, RU486. This interferes with, like, if you take this molecule RU486 within a few days of unprotected sex, it can prevent unwanted pregnancies. It has to be very soon. This is also a trademark for Plan B. So RU486 has a methyl there. It's an internal alkyne. This is a terminal alkyne. Another place you might see the alkyne is in this poisonous dart frog, and it's a defensive toxin, and it interferes with the nerve transmission, keeps muscle contraction, prolonged muscle contraction. How do you make these alkynes? Well, you do dehalogenation. I will not ask you about this. You might get it on your homework, but you have to use a very, 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 very strong base, okay? Because sodium, this is called sodium amide, okay? Amide. You could also say amide. Different people say different things. They're both equally correct. Sodium, I might do it half the time, amide. So this is hydrogen here, and this is just acid-base reaction of E2, elimination. And then it gives you the vinyl chloride. This is called a vinyl chloride. Now, you know the reason why you have to have a very, very, very strong base. This is easy to do, okay, this E2 step here. But to deprotonate this vinyl chloride, this is an sp2 carbon. It's not easy to do. You actually have to probably heat it to 200 degrees. It's really hard, and it's because of this vinyl chloride. And that's what it's showing you, why you need two equivalents. But you're also gonna, you're gonna heat this like 200 degrees Celsius to make this alkyne. I will not ask you to make an alkyne. Usually we purchase the alkynes, and now what I do want to do is show you how to do electrophilic additions. Okay, so here are some reactions you are required to know. Your starting material now is an alkyne. These are going through electrophilic addition mechanism. They're addition reactions of alkynes. Let's see if these reagents look familiar to you. HX, okay, the halogenation. We've done this already, folks, but now we're going to do it 2 times. So you're going to need to know what one equivalence, you'll see this equivalence, which is equivalence, equivalence. One equivalence means just one HX, and then sometimes you'll have two HX. So two equivalents is what we have here, because you can do two or one electrophilic additions. Here we have two equivalents, and you see you're adding halogens multiple times. This is kind of similar to mercury acetate. Okay, do you remember that in water? And then we did sodium borohydride, but notice it is not. This is actually sulfuric acid and mercury sulfate. Okay, so keep that in mind, that that's not the same reagent. So if you add these reagents to an alkyne, it's wrong. These are your new reagents for this. And then we did this one, hydroboration, oxidation, but it's different as well. We added BH3, whereas this is R2BH, because you got to tame that boron down to one hydrogen on that. But then 2 is the same. So these are 4 types of reactions that we will go over, and I expect you to be able to do. So first of all, we'll talk about the acidic nature of the alkyne. This alkyne is an sp carbon hydrogen bond. It has a pKa of 25. So if you use a strong base, you can make the, I call this the alkyne ide. Okay, so the alkyne ide. So you can make an alkynide. That's a negative carbon. That is huge. This is a nucleophilic carbon. You have not seen that really until you've seen this with CH3 and lithium or the Grignard. And those are the only times you've seen this negative carbon, this nucleophilic carbon. This is a big deal. You can only do this with a terminal alkyne. Bases that you need, sodium hydride would work and sodium amide. Usually you use sodium amide for this. And why is that? Well, when you deprotonate this, what is the conjugate acid over here for that? H2, pKa of 35. So 35 is greater than 25. And then here, this would be NH3, pKa again is 35. Something that will not work is sodium hydroxide, because the pKa of your conjugate acid is only going to be water, and that's 15.7. That is less than 25, so that's not going to work. Sodium alkoxide as well will not work, because you're going to get a pKa of your conjugate acid of about 16. So you're going to have strong bases if you want to generate an alkynide. And these are 2 examples of bases that will work. Another one that will work is LDA. And we can look at that as well. So that's what they're saying. Strong enough bases. Sodium amide and hydride, sodium hydride. And that's because they have pKa values of the conjugate acid. Okay, so if you want to add hydrohalogenation, you do have a POGL that does these reactions. And so one equivalence is going to add H, and then you get this intermediate, and you can put H on either one of them if they're the same, and then the chloride or whatever will come in and add, and you get a vinyl halide, and then you add it again. Now this is something familiar, because, and this is going to put the carbocation on the X. This is important here, okay? Because this has lone pairs, they can do a resonance structure that will stabilize that. So notice that you get the halide adding to the same carbon. So this is important This is also called a geminal dihalide because it's going to the same carbon. So that's important. So here you see the product can be either cis or trans, but when you add the second equivalence of HCl, it's going to make the geminal dihalide. HBr here, now this will matter because your vinyl halide is going to go where the bromide would go to the more substituted carbon, and then here, of course, it's going to go geminal. So this is showing you get a vinyl chloride as your first intermediate. Here's the vinyl carbocation in red, and then the halide will add, and then you get this. Now, the reason why this works is because this is a good resonance structure. You have an expanded octet where you can put your positive charge on the bromine. So that's that and that's that. So that's a resonance structure they're not showing you there, but this is why the bromide will add to this carbon. You do not get this one. You only get A. Okay, they're showing you the resonance structure here, and that's why. It's the positive charge can be delocalized and stable by resonance. And so, what if you just add halogens? So if you add halogens, you get this trans dihalide. If you remember, for the alkene, it makes that bridged three-membered ring, the halonium. And now the next equivalence, the second equivalence, is going to add across. So you get a tetrahalide there. So you're going to add it 4 times. That gives you a tetrahalide. Okay, now these are more interesting, I think, because you're going to get a new functional group. This is a new functional group that I want you to know. I think, you know that song with the, right here. Let's play this song here. See if you remember this song. What does the fox say? You remember that song? Do you remember that song? Dog goes woo, cat goes meow, bird goes tweet, and mouse goes squeak. Cow goes moo, frog goes crow, and the elephant goes toot. Ducks say quack. Okay, so maybe you know that song. What does the fox say? I don't know what the fox says. Okay, so I think of what does the donkey say? What does the donkey say? So you got to get nasally. Oh, eno. Okay, so this is an enol. It's a double bond, and then it's also an OH. So that's the ene, and this is the all. Okay, so this is enol. And so when you have an alkyne and you add sulfuric acid and water, you get an enol. And that's all you got to draw is you got to draw the enol. Now the so you make the enol, and notice this is an internal alkyne. Doesn't have to be. It could be something like this. You could get something like this, and then you would make the enol. Now for this, the enol is gonna go to the less. So we have how many carbons? 1, 2, 3, 4. So the enol 1, 2, 1, 2, 3. The enol is going to go here. Okay, so this is going to be the enol, and the enol will give you the and this is kind of like Markovnikov's. You can think of the mercury and the sulfate. It's going to give you the more substituted enol, okay, where the OH goes to the more substituted. Now, what do enols do? They tautomerize. Tautomerize. Okay, so that's a new word too. And so this is what this is. This is tautomerization. And you can go through, I'm going to show you like a long way to go through. It's actually really an intermolecular mechanism that's accepted. I do as an intramolecular because it's just quicker. But the OH goes here, and then there's where your H goes onto that carbon. And then these electrons here, they're connecting the oxygen and the hydrogen, go here to make a ketone. And that's in a new functional group as well, a ketone. So what's happening here is these electrons will go and take that hydrogen, and then these electrons will go here. And so this does this tautomerization. You can write tautomerization here. And what happens is that carbon gets the hydrogen, and then this carbon becomes the oxygen. So what does this look like without the hydrogen drawn? 1, 2, 3, 4. 1, 2, 3, 4. This is 2-butanone. Butanone. Butanone. Okay. So it makes a ketone, and it will tautomerize. So these are enols. Now, have you ever heard of Watson and Crick? Watson and Crick. What do you think of? Are you thinking DNA, the structure of DNA, the double helix? Well, let me just tell you. If you look up the history and the story about this, you'll see that Linus Pauling actually came up with the structures of the DNA bases before Watson and Crick. And he did get a Nobel Prize later on, but they did not give him the credit for the DNA structures because he did not do the ketone tautomers. He drew the structures as enols. And so enols tautomerize to the ketone. Now, at a pH of, or physiological pH of 7.2, our DNA bases are in the ketone structure. But at lower pHs and higher pHs, actually our bases, our nucleobases, go into this enol form. So there's that tautomerization. It is an equilibrium because we're dealing with the movement of a proton. That's, you've seen these equilibrium reactions when we've done protonation and deprotonation and acid-base reactions. So water and sulfuric acid and mercury acetate, these combinations give you an enol. And then the enol tautomerizes, and like I said, just go there, and then that becomes this bond here becomes this, and then this bond here adds that hydrogen there to the carbon next door. And this is an example of a ketone, and it does Markovnikov. So this is a terminal. So the terminal alkyne, it's this carbon, the more substituted carbon, that's going to get the OH. But then when it tautomerizes, and I want you to be able to show a tautomerization equilibrium here, you see it lies more to the ketone. But this double bond is going to go and take that hydrogen. So that's that new bond there. And then it's these electrons that are holding on to the oxygen that become the double bond. And so if you have an unsymmetrical, or you have a terminal alkyne, the ketone will be formed, meaning that tautomerization, you need to put the OH, the enol, on the more substituted carbon, Markovnikov. So this is showing you the enol versus the ketone form, and there's your hydrogen. Equilibrium favors the ketone largely because the carbonyl is much stronger than the carbon-carbon double bond. Tautomerization, the process of converting one tautomer into another. It can be catalyzed by acid and So this is showing you tautomerization and acid. Like I said, unless you have online homework questions about this, I'm not going to require you to show this. Um, so you do need to be able to draw the enol. On this, you don't have to draw those electron curved arrows. You just need to be able to go from here to the enol, and then you need to be able to do the tautomerization, which I'm okay with an internal tautomerization where you just go like this for time. I'm okay with that. Um, and there's your hydrogen that adds there, and then this is your double bond. And that can give you the ketone. So you need to be able just to draw the alkyne, the reagents, the enol, and then the tautomerization to the ketone. Now, these are our other reagents that give you the anti-mark. And so what happens when you take an alkyne, this is an internal alkyne, okay, we'll do an internal alkyne and we'll do a terminal alkyne. Now, I want to tell you that the other reagents, which were sulfuric acid, mercury sulfate, and water, make sure you get those. The details matter, okay? Um, that gives you always. You see this always? When you take a functional group transformation from an alkyne, no matter what kind of alkyne, it can be terminal or internal, will always give you a ketone. Okay, will always give you a ketone. That's Markovnikov's addition to make your enol. Now, you're going to see something different here because if you remember, the boron is an anti-mark. Now, it will not matter, no matter, for an alkyne because they're equally substituted. So you get your organoborane, which I would want you to be able to do that. So draw this, be able to just, and all you have to do, you don't have to draw electron flow arrows, just draw your organoborane. See the hydrogen and the BH2 are on the same side, okay? And then it's the second step that you add hydrogen peroxide and water. Now this hydroboration is going to actually be an R2BH. That's the one you're going to want to use for an alkyne. So we'll see that as well. Now you just want to replace that BH with the OH. Okay, so you just replace that. But it's going to go through a tautomerization. So here, these electrons go and get that hydrogen there. And then you have these electrons go and form the ketone. So this is a ketone when it's an internal alkyne. But what about when you have a terminal alkyne? You're going to get a different functional group. So let's look at that. Internal alkyne, it can go here or it can go there. It's going to be a ketone. But when you have a terminal alkyne, so go ahead and draw that hydrogen in there just to make sure you know that it's a terminal. Notice this is R2BH, and we'll talk about that in a minute. But this generates the intermediate. So if you were going to draw the mechanism, I would expect you to draw this intermediate. So you draw this, I would expect you to do the BH and the H here. Okay. This, well, you could do BH too. I'm okay with that, even though it's R, it's B, R, H. Now, then the OH becomes the enol. So then you can draw the enol here. Notice that the OH is on the least substituted because the BH2 is on the least substituted carbon here. The OH becomes, this is the second thing, when you replace the BH2 with an OH, it's on the least substituted carbon, the anti-mark. Now this is a enol. So now what happens? Watch this. When this double bond does the tautomerization, and these electrons here form this, you now, because you have this hydrogen here, well, we can make it red. You have this hydrogen here, this hydrogen here. This is a hydrogen. This is an aldehyde. So this is the only way you know at this point how to make aldehydes. Okay, this is a big deal. And this is the only way too, using mercury, sulfate, and sulfuric acid and water with alkynes is the only way you know how to make ketones. This is another way to make ketones, but it has to be an internal alkyne. This is the only way you know how to make an aldehyde. So if you ever have a compound where you need to make an aldehyde, you need to be thinking, I need electrophilic addition of an alkyne. All right, so there's what's nice about, and I call these instead of acetylide because I don't really like the acetyl, the alkanide, anion, is the way to increase the number of carbons on a compound. Now there's a word for this we call it homologous. Okay, so you can increase the number of carbons synthetically. And that's what we're going to be looking at now that you know all the four reactions in this chapter. We're going to spend the next few slides looking at how to use these reactions synthetically. And so the first thing you want to do is generate the alkanide anion to make the negative carbon. So the first thing you want to do, one, is probably use sodium amide is what I would use. And you have to have a terminal alkyne. So a terminal alkyne and sodium amide. Now you have made this alkanide. Now what you're going to do is an SN2 reaction. Okay, so the next thing you want to do, number 2, is an SN2 reaction. So they're showing you that. So now you get a nucleophile, and let's say you have something like this, and you have generated your alkanide. Okay, and so here you have this, and you do an SN2 reaction. What have you made? This is 1, 2, 3 carbons, 1, 2, 3, and then you've added these carbons, 1, and this is the triple bond here, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. So see, too many carbons. You want to be numbering these and counting because it gets confusing. So 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 1, 2, 3, and let's make it straight. You see, so sometimes you need a pencil because you're going to want to erase some of these. This should be as straight as you can be. So that is 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And then this is your nucleophile here. 1, 2, 3, 4. 1, 2, 3, 4. So we've made a 7 carbon chain. And that's how you increase your number of carbons to make compounds. So the first thing you have to do is you'll have to generate this alkanide. Like I said, you use sodium hydride base to generate this nucleophile, and then you do an SN2 reaction. This is a benzylic carbon here, so here's your SN2 reaction, and you got 14 carbons. Okay, so here it can also, it's really a nucleophile though, but it can act as a strong base. So here you really want to do, if you're designing your reaction, you want to use methyl halides, primary halides, allylic halides, benzylic halides. you want to stay away from secondary and tertiary because of the E2 mechanism. And so here's a synthesis in which this molecule was made. Um, and here we have the nucleophile, and it does an SN2 reaction. So you can see this is the new bond being made here to this carbon is here. And then you can do other reactions. They're strong nucleophiles. They can also open epoxide rings. So this is going to be what I would consider basic because you see you have a negative charge, so it's going to open this epoxide SN2 fashion, right? But it's going to do from the least hindered. And so then our new bond will be this carbon here and this carbon here. That's our new bond. And then the oxygen there, and then it has to get protonated to make your alcohol. Notice that it's what we call one carbon removed from the electrophile. This is the electrophile, and so this is that carbon, that's this carbon. So your OH functional group is one carbon removed. This does an SN2 backside, so it's going to show you that on a ring it's going to come in underneath. So you see that you have the dash versus the wedge, and that would be trans. So retrosynthesis analysis, this is where we have our target compound, but we got to work backwards. And there's your open arrow, and you get precursor, and you can do lots of these, and you get to your starting material. One of my favorite things I did I worked at Eli Lilly. Sometimes you might see Lilly like that. Okay, it makes different molecules. I worked for 6 years in R&D, and my favorite compound that I ended up ultimately making was 18-step synthesis. Okay, and it was for it's called benign prostate hyperplasia. It's for enlarged prostates, but it did actually go to clinical trials and stuff and did get a Lilly number. What a Lilly number is so when you make compounds, I actually was NF7, so they give you these acronyms, so anything you ever make, it gets a number, and then you get this 3-digit code, and that's who you are. I was NF7, okay? And this has been a long time, and I still remember that, but if you get a compound that goes into clinical trials, they drop that, and they will put their number at Lilly. So you'll get a Lilly number. You might see this in different compounds like GSK. I'll have a GSK and then a number. And this is how they number compounds and stuff like that. But the reason why I bring this up is because this is, if you're making compounds and you have a target compound, this is where you're actually starting. And for me, I started here, and then I had to work back, and like we're talking 18 steps to make this compound. And the problem is you get the starting material and you figure out what starting material, and you might get here and be like, oh, it didn't work. And then you have to go back and rethink this. So, and you use these different reagents. And this is retrosynthetic analysis. So how do you do this? You want to think about the functional group transformations, FGT, functional group transformations. And you need to know these different ways to be able to do an alkyne, for example, to an aldehyde. So if you need an aldehyde, then do you know how to go from an alkyne to an aldehyde? And so you work backwards because you're like, okay, well, what functional group do I need? And you just keep going backwards. So hopefully we can have a few slides to illustrate that. So here, if we want a ketone, well, you have 2 ways to make a ketone. And both of these ketones, what you know, come from an alkyne. So if you could do so you have something like this, and then I would draw this out to make it linear, 1, 2, 3, 4. Okay, so this, here we have, and then you can go forward. Okay, so I need an alkyne. So I've got 4 carbons, I've got 4 carbons, I've got 4 carbons. So you're counting carbons a lot. And then you can say, okay, well, going forward, how do we do this? Well, we can do this with mercury sulfate and sulfuric acid and water. And that would be way. What if you need to add 2 carbons? So what if you started with this compound? Okay, what would you do then? So if this is your starting material, well, you would have to use sodium amide to make a carbon anion, and then you would have to do an SN2 reaction so you can get 4 carbons. Okay, so that would be your SN2 reaction. So this would be your starting material. And then going forward, and then you could go the mercury sulfate and sulfuric acid to give you the ketone. So backwards and forward. And this is showing you exactly that. Here we have sodium hydride, which generates your carbon anion. This is a 2 carbon, so we'll count your carbons. You need a 4 carbon target. So here, this is these 2 carbons here, and then you can say, okay, well, and these 2 carbons are going to come from the alkyne because we're going to get the ketone. So we can go from a alkyne functional group to a ketone. So we got to think about the functional group transformations, and this goes through the enol, which is this compound here, and there's your 4 carbons. And so then you can do an enol tautomerization where you get your ketone. And that wraps up the electrophilic addition reactions of alkynes to give you different compounds.